All right, this is physics reaction video number 20. This time I did a search for quote honors physics unquote, and this I think may have been the first hit. And I put a filter on this week. Why not? Let's get something fresh and new. And I had to fast forward about 3 minutes in because it turns out that this was actually a Zoom meeting at first where he was talking to his students, but I believe this is the moment when he starts working a problem. So we'll see. If that's not true, we'll do something else. All right, here we go.
All right, so notes for today, you can label circular or uniform circular motion. So let me pull up my other camera.
Well, I like that labeling, encouraging them to use the exact right phrase maybe at the top of their notes or something.
All right, so notes for today.
Oh, okay.
Uniform
so 2 cameras.
Circular motion. And we're going to find that there are a lot of places where this has application.
Can't see the other camera in this shot.
The most obvious ones might be we're eventually going to be talking about satellites, right?
Satellites.
Whether they're man-made satellites or whether they're things like the moon or how the Earth goes around the sun or things like that. So we're going to get into that this unit. But then even some more terrestrial things like how do you turn in a car? Because if you think about turning, what you're really doing to turn is you're just kind of going in a quarter circle, right? So if I want to turn left, I kind of am doing a quarter of a circular motion. So that's...
Yeah, students have way more experience doing a quarter circle than they do doing a whole circle in a car. That's actually really, really cool.
Kind of the idea for this. What we were originally going to do today in class was we were going to do a lab with my flying pigs. I just want this here. Let's see here, so that you can see.
Oh, that's cool.
Got here. So
he's quite adept
to introduce the idea of circular motion, I got these little pigs that are tied to the ceiling. And
awesome.
They do something like this, right? So you should be able to see, right? So you can kind of see that there's a cord on this here, right? And the idea is I want to analyze what it is that makes the pig go in a circle, okay?
This is really, really great because I think that the answers that might be in his students' minds are all over the place. So some will be saying, oh, it's the cable. Some are going to be saying, oh, it's the wings, it's the flying. Or some are going to be saying, because it's turning. Right, it's not 100% clear that this pig is symmetric. So when he first let go of it, it turned right. But I'm guessing that's because it was, angled out. Whichever way, angled out, when he grabbed it and threw it. But I'm sure there's students who just think of like if you make a car go round and round, you would take the wheels and you would turn them. And so the idea that it's the tension of the wire that's actually forcing that right-hand turn is subtle, right? I think the other thing that's interesting about this problem is it's really a 3-dimensional problem, right? So the tension is up at some crazy angle, then you've got gravity going straight down, and together they're making this horizontal force, which just seems so weird, right? But you get the students, you say, well, is it falling? Well, it's not falling. Oh, is it rising? Oh, it's not rising. Oh, well, then the vertical aspect of gravity's force must be dealt with by somebody. I think that's really, really interesting. I'm also intrigued by the fact that it has wings. I don't think this has to have wings, right? Well, maybe it does, because I suppose if he had just thrown it, it would have decayed a little bit faster than it did. So that's really interesting. It has some self-propelled motion. So you have to deal with that too. So I think this is a really, really great way to start the class. One of my questions is, and what I'm going to watch for is, how does he sort of maintain that complexity? Does he very quickly say, look, we're only going to look at this aspect of it? Does he sort of keep track of all of it, knowing that it might be in his students' heads? How do you deal with the expectations of your students who are thinking about all of these things? Because if your answer, let's say you get a numeric answer or something, if your answer doesn't sort of address what the students got excited about, it feels like that's a problem. I mean, they might be able to go home and do homework problems, but can they really explain what they saw? So I think that this is a really, really cool setup, and I loved how adept he was with futzing with his cameras.
So that's what we're going to look at. Turns out you need two things in order to go to a circle, in a circle.
Now he's going back to the other camera, I bet.
First thing,
Oh, there we go.
what am I going to say here? I'll just say two ingredients for circular motion.
Oh, I like that. I like that a lot. I use the phrase hallmarks a lot.
And the first...
But hallmarks, I use that phrase, the hallmarks of circular motion are, hallmarks are things you watch for. Ingredients are things that you bring to the table. So there's a difference there, right? Like witnessing something that's going in circular motion and watching for the hallmarks versus let's make something go in a circular motion. Much more of an active plan. I'm going to file that away. Ingredients, I like that. What do you guys think? Ingredients versus hallmarks.
Is you need to have some sort of forward velocity.
Ooh.
So in our case, with the pig,
cool.
right? I wish you were here so that you could see it. We would have done a whole lab with this. But the idea was the wings on the pig. The purpose of the wings on the pig is to continue it going forward.
Cool.
These wings aren't providing any lift, but they're making it go forward. So you got to have forward velocity to have circular motion. And the second thing that you got to have is you got to have something called a centripetal force, which is a force directed towards a fixed center.
I like that. So he said centripetal, but he didn't write the word down, at least not yet.
And again, we're going to refer to that as a centripetal force.
Let's count how many times he says centrifugal. I'm going to guess 0.
Okay. I like to think about circular motion as a fight between these two influences, right? You have them both in equal measure.
That's cool.
And if one of them starts to take over, you no longer have circular motion. So I'm going to give you an example here. I'm going to show you a YouTube video.
Oh. Wow. Inception here.
Not that one.
I can't help myself. I always look at people's bookmarks.
My way so that I can click on something.
Wow. Look at all those bookmarks.
Make sure you can. All right. So you've probably seen one of these at a museum or something, right? Where you put these pennies in here.
Boy, I remember the first time I saw one of these. I wanted to stay there all day. I thought it was so cool.
And the idea is that surface, right? The fact that surface has a funnel means that you've got a normal force that's giving you your centripetal force, right? But you'll notice you need both things to have.
So this is tough, right? This is COVID teaching, right? 101. So if you wanted to display a video, you saw how choppy it is, and probably my recording of my screen is making it even choppier. In this case, very, very likely they've experienced this, and so it's fine, right? Because they can sort of remember, oh yeah, I remember how that works, and I know what that's supposed to look like. Certainly that's what's happening to me. Quick little story. One of my kids, when he was very young, would really get hyped up before dinner. Just really the energy would start to spin, and he would be, going crazy, doing stuff all around the house, and then, man, he would just fall asleep. And it was just remarkable, especially, my other kid at the time, we have 3 now, but at the time we just had 2. And the other one, it just took forever to fall asleep. But the second one would just, really get wound up and really excited, and then boom, fall asleep. And it was remarkable to watch. And I remember saying to him, you're like this, because this funnel thing, it just goes faster and faster and faster and faster and faster, and it pops. So that's what I always think of when I see these. So this sharing screen stuff, sharing movies, we all know that it's a struggle. If you've got a live thing, I'm a little bit surprised he didn't. Okay. I was going to say, why not just send the link to your students? It's a Zoom meeting. Send the link and have them watch it on their own. That definitely gives you better quality, but you don't have the control over where you might pause, what you might point to, what you might say. They're all a little bit out of sync with each other, so you can't say things like, did you just see that? So, this is a great way to do it, especially if it's something they've very likely seen in real life.
circular motion. You have to have the centripetal force, which in this case is coming from the normal force of the bowl, but you also have to have forward velocity. You can see earlier in this video when the two pennies, there, you see that when the two pennies knock into each other, right? What's happened is now they've lost their forward motion. So if you lose your forward motion, all that's left is the centripetal force, and you end up going towards the center, right?
That's cool.
So I'm gonna add a little bit to the notes here.
So as I recall, there's XKCD, the webcomic, talks a lot about what it means to fly and launch rockets, and it's all about sort of being able to go around fast enough, right? So if you just go up, it's not enough. You're just going to fall back down. Also, I loved doing projects with my students, or homework problems, where you say, okay, you're going round and round. Well, how do you fall straight back down again? Well, the G.I. Joe movie says you just open your bay ports and drop these missiles. Nope. You have to fire them backwards amazingly fast to get them to be at rest so that they then fall. So if you just open your bay doors, so many movies get this wrong. What was the other movie I was watching recently? Same problem. They just open the bay doors, and it's like, no, that's not going to do anything. What do you think happens? Those guys let go of the insides of the shuttle all the time. They don't get smashed, and they don't drop to the earth. So this idea that when the pennies smacked each other and they lose their, what did he say, step one, their forward velocity, boom, then they just fall down to the center. I thought that was actually a really cool way of talking about it.
This. What I want to do here is I kind of want to draw an object that's moving in a circle. So I'll just draw this object at 3.
I learned from a math professor, draw the circle first, then the center later. Don't draw the center and then try to draw the circle. Very good lesson.
3 different locations.
Ooh, that's a good idea.
Each time it is moving forward. Right? So I'm going to draw a velocity vector that is constantly changing direction. And then it's also going to have this thing called a centripetal force, which I will label as FC. And the centripetal force always needs to be directed towards a fixed center.
Man, that's such a great job. Perfect circle.
Grab the next demo.
Great vectors. Man, really, wow. This is quite symmetric. It's really great.
So the pennies kind of show what happens if you lose your forward momentum, right? Or you lose your forward velocity. If you lose your forward velocity, where are you going to go? Going to the center.
Yeah.
But the other question is, what happens if you lose your centripetal force? Well, if you lose your centripetal force, now all you've got is your velocity, and you're going to go in a straight line. Right?
That's cool.
So I think about this like the David and Goliath sort of slingshot, right? If you think about, if I've got something on the end of a string that I'm putting in a circle, right? It's got some sort of forward motion, but the string right now is providing centripetal force. Now, if all of a sudden the centripetal force leaves, right? So all of a sudden I let go of it and I don't have a centripetal force.
That was great. So here's what I was thinking while he was doing that. I'm like, I know he's going to let go. Is he trying to figure out exactly how to let go of it? Is like he doesn't want to hit the ceiling. He wants it to be in the frame. My guess is he wanted it to go that way, which is exactly what he did. And did you notice that the rate that it was going around kind of slowed down? It was because he was thinking about it. So that was really remarkable, right? So keeping his stream of consciousness going, really continuing to be able to talk about what was going on, while at the same time trying to figure out exactly how to get it so that when he lets go, it doesn't hurt anybody, it doesn't hit the camera, it doesn't do anything else. Reminds me of my soccer juggling record. I really wanted to juggle the soccer ball over 1,000 times, and I was going and I was doing great, and I was in the 800s and I was in the 900s on my driveway. All my neighbors thought I was crazy, but I just really wanted to break 1,000. So I got over 1,000, and I realized, wow, I'm doing so great. I'm so excited, but I had to concentrate. So I'm concentrating. I'm keeping my legs going, keeping the ball bouncing up without hitting the ground. I'm counting, right? You constantly have to count to not lose track. And celebrating. And suddenly I'm like, wait, I need a number that I can remember, right? Because if I'm setting this record, I want to tell people about it for years. So now I'm counting, I'm juggling, and I'm trying to think of a number that's coming up that would be useful to be able to remember. And then I had to make sure I made it there. So it turned out that the number I came up with was 1122. Had to do with one of my kids' birthdays. And I'm at about, I don't know, 1,050 or so, and I realized I needed to go another 77. I mean, imagine how complicated all this thinking was. And watching what he just did there with a live audience was really, really cool. And he nailed it. I mean, I'll bet you anything it went exactly where he wanted it to go. I really thought that was great.
What's going to happen is the velocity is going to take over, right? So you have to have both of these things in order to have projectile motion.
That's really great.
Okay.
Really emphasizing those two things.
Not projectile motion, circular.
That was really, really cool.
All right. The next thing I want to say about that is I want to give you two equations. So
Switching the camera again.
Centripetal force, and usually you can have more than one force that gives it to you. Someone will say it's the centripetal net force.
Oh, that's cool.
So the centripetal net force, and sometimes your book will refer to this as the radial force as well, because it points along a radius.
It's interesting when he puts it in quotes like that. Sometimes we put things in quotes to be a little bit derisive of it, right? Like, well, it calls it the radial force. But I think it's so important to connect it to the other resources that your students have. If they've got a book and the book is saying it, you have to connect it. Otherwise, they're going to be like, what? You were talking about centripetal force. I couldn't find it. But I've found in my teaching that students appreciate when there's slight deviations from the book so that you can say, look, there's a couple of different ways to go after this. I'm used to calling it this, but you can also call it that, rather than trying to make the students feel like they're being indoctrinated, like you have to call it the radial force because the book said so. So I'm all for this, but I do think that you have to connect it just as he's done it here. So very cool.
But I prefer the term centripetal force. But net force is equal to mass times acceleration. So we're going to say that the centripetal net force is equal to mass times the centripetal acceleration. So this is one equation for you.
Cool.
And the other equation is the centripetal force, the centripetal acceleration equation, which is v squared over r.
Yeah. Did this come out of nowhere?
Now, where does this come from?
Okay.
Again, because we got shortened time, I don't want to go into this, but I've recorded a bonus video if you're interested.
Wow. Now that was cool. I really liked what he just did. He said, okay, it's COVID, folks. I didn't do it the way that I normally would have done it, where I would have derived this. But I'm trying to tell you these are our two building blocks. This is what we're going to just spend a ton of time doing. And he said, look, there is a derivation of this, and I've made a whole other resource for you to be able to follow that. And I love that, right? Because there are some students who need that curiosity satiated right now, right? Where they, oh man, I got to watch that video because what the heck, v squared over r, that doesn't even seem to have the right units or whatever. And I think that to know that he has an opportunity to make other resources that he can record and send to them is interesting. I will often pull my students in class, and I'll look at the clock and I'll say, you guys, we have 20 minutes left. And we're kind of starting this derivation, and I'm going to tell you that the answer is really cool. The result of this derivation is awesome, and I'm going to hold you accountable for two things. I'm going to hold you accountable for the derivation. I'm going to hold you accountable for being able to use the result in some of your work. So we've got 20 minutes right now with me. Do you want me to finish this derivation and then just assign some problems? Do you want me to stop and work some problems and then give you a video about the derivation? And usually the debate is pretty robust in class because there's two different types of students who just want to get their homework done. They're like, oh my God, please show me some examples. I don't care about any of this, which is why you'll note that I said I'm going to hold you accountable for this derivation, which they know that means I'm going to make them make a video for me explaining it, right? So they know that both are important, but I love letting them sort of fight it out in class. I'm like, look, you guys, we only have 20 minutes. I can only do one thing. And the other thing I will do is a video. So I'll either do some problems as a video or I'll do the derivation as a video. And I love to give the students that agency to talk about it. I know that, fundamentally it'll all be there for them. So I'm not too worried about it. But I really he made a choice. And obviously he made this choice before he started the video. And I think that it's a really, really interesting choice. Let's see if he says a little bit more about it.
On Schoology to figure out why that's the equation. But these are sort of the two equations you need to start out talking about circular motion. So I could do something then like ask you.
All right, I'm actually going to stop right there. It's a good time here. So lots of really cool stuff in here. I love his number 1 and number 2. So this forward velocity and a force directed toward a center. I loved how he called it ingredients. I'm fascinated by that. And because it feels so active. I'm going to go make something go in a circle. And I loved how they fight against each other, that if you lose one, the other one wins. And the two examples that I gave I thought were great. I think his use of video was cool, though, a little bit fraught with the technology, with the pausing, although that may have just been because I'm recording my screen. And I loved the decision that he had to make. I don't love the fact he had to make a decision, but he had to make a decision, right? And so he could have just done this in this video and then gone on. My guess is he's about to do some problems or something. But I think that these are exactly the types of decisions I like to watch teachers make. And then, of course, the remarkable mental agility to talk about centripetal acceleration, to talk about things going in circular motion, to spin something around in your hand, to contemplate the speed that you want to do it in, and be able to let go of it at exactly the right moment. Very, very cool. All right, you guys, have a great day. Thanksgiving's coming up here in the United States, so I hope that you all stay safe and enjoy that. And otherwise, remember, physics teachers are awesome.